Hello, this will be an overall review of Unit 2 of AP Physics 1, and this is the updated review for the new AP Physics test. So before I go into this is just an overall review of what we're going to see. If you guys do want more specific videos, please feel free to leave it in the comments below. But with that, let's go first into this. So with all of these physics questions, you're gonna have these types of forces. Now, what makes it tricky is how these forces react with each other. So let's go one by one and talk about what each one means. The first one we have is a gravitational force. A gravitational force is basically the force of gravity. It's written by Fg, but it's also sometimes seen as just capital G or whatever they give to you in the specific problems. And remember, with these, if they do give you a specific variation of the force of gravity or any of these forces, if you're doing the free response questions, you want to keep that exact same notation that they have. So now with this, how do we actually see gravitational force? Well, gravitational force is seen in a bunch of stuff. If we were to have a box that's just sitting on a table that's on Earth, you have to assume it's on Earth, then there's gravitational force getting pulled down to the ground. You'd write it as Fg like this. Or in another circumstance, if we have this point as Earth and we're orbiting around that, there is what you call a force getting pulled down. Fg is getting pulled at every single direction, is getting pulled towards the middle. In every circumstance, you're going to have force of gravity. And in all of these here, except one we'll get into, they will have some sort of reaction with force of gravity. So let's look closer into this box. Right now, what I have driven makes no sense because when you're looking at this, you want to look at how the forces act. So right now, all I'm saying is that there's a force of gravity just getting pulled on the box. But that doesn't make any sense because what I'm saying then is that whenever I have a box on a flat surface with no forces acted on it, it'll just get put straight into the middle of Earth. Well, we know that's not true. So what that means is that there has to be another force that cancels it out. And what is that? That'd be right here, this normal force. So on this, the normal force is always perpendicular to the surface of the contact. It is written as Fn, or sometimes just written as any other types of force, but it's normally seen as Fn. The special thing with normal force is the fact that it is specific to how it's drawn. It's drawn to always being perpendicular to the force of applied action. So what that means is here, the force of gravity is already being pulled down here to the bottom. So then that means it's in respect to this line here, which is just the ground. So then that means the force of Newton or the normal force will be guaranteed to be pulling up. Now, this makes a lot of sense. What this is basically saying is that these lines you see here are saying that they're equal to each other. So what this is that Fn is equal to Fg, which makes sense because if both of those forces are equal and they're in opposite directions, then that means they cancel out. So then that means the box stays in rest, which is exactly what's going on. If you put a box on the table with no other forces getting acted on it, the gravitational force and the normal force is taken out of the equation and thus they would cancel off each other. Now, let's look into tension force. Tension force you see so far in Unit 2 as this sort of object. You would have this is the ceiling, you would have a string or any type of rope and a box like this. So from here, we know that the string has to be pulling up on the box, right? Force of tension, because the string holds the weight of this. But then remember before how with all of this, there will be a guaranteed gravitational force that's being pulled on the object. And gravitational force is always equal to the whole mass of the object. So what that means is the force of gravity will be equal to the mass times the gravitational pull. Now, in this case, if it's assumed to be on Earth, this gravity will be read as 9.8 meters per second when you want to be specific. So, an example of this is on the experimental design FRQs for physics. you'd want to use 9.8 to get as close as you can to the right answer. But if it's not necessarily wanting to be specific, but more seeing the steps, then you can just write it as 10 meters per second. And it would be meters per second squared because this gravity is a type of acceleration. And if it's not on Earth, they'll give you the gravity for it. You do not have to calculate it, or sometimes you might have to substitute for it. Now, let's look towards friction. With friction, if we were to have a box and we apply some force that causes it to move to the right, then the reason that that box slows down is because there's friction getting pulled to this opposite way. We'll get more into friction because it has a special equation designated to it. But what we're just trying to see in this case is how do the forces look? With this unit as a whole, the biggest thing that we want to see is how are these forces getting acted upon each other. So let's go into this example here. If we were to take this box and we'll just assume that that box is this dot. So now what you want to do is to clarify whether forces are in the vertical or horizontal direction. For example, if we see here, always remember that there's a force of gravity. So we know we can write a force of gravity arrow going down, but also remember that the box isn't moving up or down. So then that means there has to be another force that counteracts force of gravity. And that would be that normal force we're talking about because we're on a surface and that surface is acting against gravity. So we write it like this. And when you do these, what we call free body diagrams, we'll go more into that in this video. When you do these, you want to get as close as you can to showing that the arrows are the same length because on the actual AP exam, they look for magnitude in these problems. Now, we have to remember this. I push the box, correct? But when I'm drawing a free body diagram, I'm not drawing the free body diagram when I push it because I pushed it for 1 second. So if I pushed it for 1 second, then there's no force applied, which our second one, but there is a frictional force. So the frictional force will be pulling away from the box. However, let's say that it was a constant force being pushed, right? So let's say in the problem it says as a constant force being pushed to the right with friction still applied. Make sure you don't assume that there's friction there and that it says that friction is negligible, which means that there is no friction, or if it doesn't state that, then there is friction. But if I said that it was a constant force being pulled to the right, being pushed to the right, then that means we would have to go into our next problem, which is force applied. Force applied is any force that's pushed, pulled, that is acted on that object. Now, what we also have to do is check where this is going. We know that this box is moving to the right, so that means that in this problem here, only this free body diagram, if it's a constant force, sorry, I have to draw this arrow larger than this one because the total system is moving to the right. In this one, since this is no applied force, I just have to write this force of friction. We'll get more into that with one of Newton's laws, but that's just one thing to think of. Now, well, that's exactly what we're going to get into, Newton's laws. So inertia is what it's called, but this is the first law is basically saying that if an object is in motion and has no sort of force acting on it, it will stay in motion until any force is acting on it. So I said a bunch of gibberish, but let's think about it visually, right? So let's say I have a box that's on a force with no friction. And let's say that I initially push it to go to the right. Since there's no friction acted on this surface right here, it will constantly be moving in the right direction because no forces are acting on it to repel its motion. Now, let's say that there's friction, right? Let's say that it's friction, it's rough and everything. Now, when I do push it, like we see in real life situations, it will slowly come to a stop because the force of friction is pulling in the opposite direction. There's a force that's acted on it. Now, let's get into our second one. Second one is really just an equation. It's force equals mass times acceleration. But notice this symbol right here. What is that? It's called the sum of forces. So what that means is that this equation can be written down as F1 plus F2 plus F3, so on and so forth, will equal to the mass times acceleration. So that means that it is the accumulation of all the forces. But remember that some forces can be positive or negative. Say that we have a force that's applied that is much more greater than its frictional force. This is a positive force, but this here is a negative force. So then when you do add them, sometimes you might be subtracting forces off of each other. It depends. Normally, up and right are both positive, but down and left are both negative. And what they like to do with this problem here is they really like to calculate for this acceleration. This acceleration is the acceleration of the system. Remember that. Remember, if it's asking for a specific object, you look specifically there and seeing what force is acting specifically on that. But if it's asking for the acceleration of the entire system, you accumulate all of the forces. Now, number three is more like an ideological thing I like to think of. It's to justify how everything works. So, reaction forces. So, before we are talking about how there's an FG and there's an FN. However, if I push down on the ground, I'm not just crushing the ground. That's not possible. The reason is because when I push down on the ground pushes up on my hand. That's called a reaction force. It's saying that every force has an equal and opposite force. That's why you can't simply just crush a wall by pushing it because the wall pushes back. They like to test this idea not on FIQs, but MCQs. When I took the AP exam myself, a very similar question was when a ladybug was walking up a wall, what are the reaction forces acting on that ladybug? So just pretend that this is a ladybug, a very beautiful ladybug. But when the ladybug pushes down on the wall, that's one reaction force already, that the ladybug pushes down on the wall. We'll call it just ladybug. But then the wall pushes up on the ladybug because as the ladybug pushes down on the wall, we already talk about that opposite force, which is that the wall pushes up. That's exactly how the ladybug goes. The ladybug goes up because the wall pushes it up. So the second reaction force is the wall. That is a very popular MCQ questions that we see. So now let's talk about FBDs, which are called free body diagrams. Free body diagrams are guaranteed to be on your FIQs, and they're a necessity. So with free body diagrams, there's two ways that you have it. You have a forced body diagram and a free body diagram. Let's first talk about the free body diagram. As you can see here, all of these lines that I was drawing, all this purple coloring that you see are free body diagrams. A free body diagram will have a circle in the middle, which is the system. And from there, all forces will be pushed out in every direction. But there's one thing that you need to make sure you do. Sometimes forces will be put diagonally like this. For the AP exam, what they want you to do is to write it like this. Write it how it shows. But in order to solve for it on another sheet of paper, what you should do instead is to break it down into its components. If we have something that's angled towards the right, we know that a portion of the force goes up and a portion of the force goes to the right. That is called breaking down forces. This is something that if it wasn't a review, I'd go more into and I'll make a clarification video for this. But this is how you write it, and this is one of the biggest things about forces, is to be able to break it down. That these two are the exact same thing, but this one here is guaranteed to have to be on your free body diagram. Now, let's talk about force diagrams. Force diagrams are similar to systems or to free body diagrams, but not everything originates from the center. Forces look exactly at where the force is acted on. For example, if we have a box, the force of gravity is from the center of the mass. So that's how I'd write it. From the middle of the box going down is the force of gravity. However, with a force of the normal force, it acts from a surface. So it acts from the surface that's in contact with both the box and the ground and gets pulled up. So the big difference between the two is that a free body diagram will start from the system as a whole and will just be pushed outwards. Remember that all the areas have to be being pushed outwards and none of it can be pointed inwards. With a force diagram, on the other hand, it will have to be from the exact point from where the force is applied on the object. For example, here we see that the mass goes from the center of mass down, but the force, the normal force, is from the contact between the box and the bottom of the ground and is being pulled up. Now, what they really like to do with forces is that they like to test you with friction and inclined planes. With friction and inclined planes, what they like to test you is how well can you break down these forces. So, before we go into that, let's look at the equation of force of friction. Force of friction can be seen as this, or force of friction, but this is what you call the coefficient of friction. Basically, how frictiony is your surface? The higher the number, the higher the force of friction is. And they love to ask you to calculate this by calculating this normal force and having this force of friction. Remember that this normal force will sometimes be broken down as components. For example, if we look down here in this system, we notice that the biggest thing that we see is that first we don't really know what's going on. Like right now, we just know is that we have an inclined plane. So what I like to do is I like to think what forces we have. So the first thing we know is that we have gravity. And remember that gravity always gets pulled down. So it gets pulled down sideways like this, but that makes it a little confusing. So a really good way to do this is that notice how it's a little slanted. So we know that there's some gravity going down here, which we'll call mgy. And we also know how there's some gravity going like this called mgx. This is why it's so important to understand how to break down forces because now we broke a force, which I'll put in a different color, as this, as normal mg, into mgy and mgx. And you'll see exactly why we did that. The reason we did that is because when we draw it out, the force of friction will be applied in this direction. When it does get applied in that direction, what that means is that it counteracts some of the mass that's applied. But as this object is falling, we have mgy being pulled down, and we also have mgx that's getting pulled down. So what that means is that the force of friction will be applied to some way to the mg. We have mg getting pulled down like this. You have mgx, which gets pulled up like this. Oh, sorry, it could be pulled down, sorry. Yep, it'd be pulled down like this. And then you have mgy, like that. mgy and mgx. This is how you'd write it. So notice how the mass will always be pulled to the bottom. It does not get affected by the angle. That's my that was my problem. I messed that part up, but mg always gets pulled down. It doesn't get put at any angle. From that center of the object, it gets pulled straight down. However, it's at an angle. So then that means you have this mgy here. And then let me write in a different color. You see that this blue, which I'll write, you see that this blue that I have written right here, that's mgx. And notice how mgx goes across f force of friction. But mgx can also be written as f of n. So that's why we see that f of n right here. Because on an inclined plane and any other plane, you'll see that force of Newton is counteracted to the force of friction. With this, an important thing to understand is that the coefficient of friction will always be less than 1. If you get a coefficient of friction that's in the thousands, then you know for a fact your answer is wrong. A good fact to just know is that the coefficient of friction is normally always less than 1. Sometimes it'll be greater than 1, but if you do everything properly, it'll never be greater than 2, but it'll also never be really around 1. But another thing to understand with this equation is that they love to test you on how well can you get the force of friction and can you apply it to this. With this, it takes practice and we'll do practice problems over and over together. But a good thing is to understand mu Fn, which is on your formula sheet. Now, the last thing we go through is tension. As we saw above, one of the forces is called tension. Right now in Unit 2, tension is pretty easy. It gets really weird when it comes to torque, but Remember that tension is with a string, a rope. It'll tell you when it's a tension force. You do not have to assume, but if it's a string or rope, you assume that there's some tension applied. With tension force, in this example here, which we've seen before, we've seen that it's a simple string just holding up all the weight. But what they like to test you on the MCQ is, let me get a better color, is sometimes they'll ask you how is the forces applied to this. Now, this is one of the relatively hard questions, and it takes some understanding to do. But with this, we have to understand another thing is to break down the forces. We know that we have T1 and T2, and then we have to understand that T1 has a force that goes in this into the right, which I'll write in pink. We know we have force that's pulled to the right, and we know they have a force that's being pulled up. And the exact same thing here, one that's being pulled to the left and one that's being pulled to the um pulled up. So basically, when you see this type of question, which it'll probably appear on your MCQ, you have to understand to break down the forces. I'll do a whole separate video breaking down forces and understanding this, but so far that's all of Unit 2 in one big whole condensed review. If you do want to see specific videos, I can do that. But if you have any questions, leave them down in the comments. Thank you so much for listening, and I can't wait to see you in the next one.